Okay, ready, Frederik? You go ahead.
Thank you so much, and thank you for having me and including my paper. So the paper that I will present is called Causal Non-Causal State Space Models and the Modeling of Financial Bubbles. And I mean, the usual disclaimer: this is work in progress here. So I thought it was a good idea, at least. I mean, Gabriele made a very nice explanation of this, but to those of you who didn't attend Gabriele's talk earlier, I thought it was a good idea to have a brief introduction to these. What is a causal model? What is a non-causal model? And why is that we bother considering these non-causal models? So now if you consider, like, this is time series analysis 101, right? If we consider now the causal autoregressive model where yt depends on the yt minus 1, so the past, hence causal. And if we model this by some heavy tail error, so here it's taken to be Cauchy, and simulate trajectories from this process here, what we observe is that, for instance, we have a large positive shock and it decreases exponentially, so it decays out, right? So this is, again, as I said, time series analysis 101. But now if we reverse the time, so instead of going, say, from left to right, we go from right to left, what we observe is that we observe an exponential increase followed by a crash. And this is exactly the kind of trajectories that you see if you consider now these non-causal autoregressive model where yt depend on yt plus 1 instead of yt minus 1. This model was originally considered by Gurion and Sakoyan and started a literature on these non-causal models here. So many economics and financial time series are characterized by such a local explosive increase followed by a sharp decrease. And one example is stock prices, where this phenomena can be the result of a bubble that bursts. There's recently been an increasing interest in mixed causal, non-causal autoregressive models with heavy tail errors to model such bubbles, for the reason that I just explained, that you can actually model these kind of behaviors with a linear model. Causal non-causal state space models with heavy tail errors have, however, received much less attention in the literature. So in this paper, I study causal non-causal state space model with heavy tail errors, and this is the main selling point of going from mixed causal non-causal autoregressive models to causal non-causal state space models, is that in contrast to mixed causal non-causal autoregressive models, we can actually model bubbles with a model that is consistent with the rational expectation stock price model, which I will now show. And with this motivating example, then I will discuss the general causal non-causal state space model. I will discuss a specific causal non-causal state space model and apply it to in the end. Okay. So just a recap slide. So in the following, I will use the stable distribution quite frequently, or use it very much. So we denote by this x, we use this notation to say that x follows a stable distributed random variable, which is characterized by 4 parameters. So it's characterized by an index of stability alpha, which determines the tails of the distribution. So if alpha is very close to 0, we have very heavy tails, and if alpha is close to 2, we have lighter tails. By a location parameter, a scale parameter, and then an asymmetry parameter, which the important thing is here is that, for simplicity, if we take mu being equal to 0, if alpha is less than 1 and beta is equal to 1, then this stable distributed random variable takes only positive values. Okay. So to model bubbles from a probabilistic point of view, Christian and Jean-Michel considered this this non-causal autoregressive model, which the one I showed before is a special case of this one. So the question is now, okay, this is like a probabilistic model, but how do we model bubbles from a financial point of view? So what does finance theory tells us about bubbles? And to answer that question, I'm going to take a step back and leave the realm of these non-causal models here. So the arguably most fundamental, let's say, discrete time model of stock prices is what is known as the rational expectation stock price model, in which the price of the stock PT is given by this equation 1 here. So it solves this equation 1, where R is equal to the expected return on the stock, ET is the expectation condition on the information at time t, and DT is the dividend. So this comes from rational expectation plus a no arbitrage argument. If we solve this equation 1, what we obtain is that the price consists of two components. It consists of a fundamental value ft, and it consists of a rational bubble bt. So the fundamental value here is a function of the expectations to the dividends or the fundamentals. And then the bt is a rational bubble which satisfies two conditions. So the first, equality, and then the second, inequality. So it's a submartingale which is strictly positive. Now, to make this operational, what one can do, or one do is that by model either dividends or the expectation to the dividends and model the bubble to make this model operational. And in the literature, many authors have argued that the expected dividend growth rate is both time-varying and persistent. So in the paper and this presentation, I will therefore, in the same vein as Van Binsberg and Kuijgen and Andreas Lambro, assume that the expected dividend growth rate follows a first-order Gaussian autoregressive process. Then we have modeled like the fundamental value here, or we have modeled like the expectation to the dividends and hence the fundamental value. And it turns out that under this assumption, we can write the spread being the difference between the price and the scale dividend as follows. So it has two components. It has a fundamental value, which is a Gaussian process, and it has a bubble satisfying the conditions as before. Okay, so this is the rational expectation stock price model under this assumption here. So if we compare it to the non-causal autoregressive model, intuitively, we need to add a component to it, right? This is a pure bubble process, and we need to add a component to it to make it consistent with the rational expectation model. So if we do that, we end up with what is known as the causal non-causal, what's called the causal non-causal convolution autoregressive model. Also briefly considered by Goriot and Sakoyan, in which now you can see if we add a component, so we see yt here is now a function of both xtf, which is a Gaussian component, and so Gaussian fundamental value, and xtb is a bubble component here as before. So now we have made the model. We have gone from the pure non-causal autoregressive model to the causal non-causal convolution autoregressive model. And the question we should ask, okay, is this model actually consistent with the rational expectation model above? And as I just told you, okay, it consists of two components as this model here, the Gaussian component here, or the fundamental value is a Gaussian process, which is also the case here. But it might not be obvious that the non-causal autoregressive process here satisfies these two conditions here. It turns out actually that it does, and to prove that, we need the following proposition, which is part due to Goriot and Sakoyan, and part also due to me. I prove it in the paper. So the first if is proved by Goriot and Sakoyan, and then the second if. So this if is proved by I proved that in the paper, and the second if is actually what you need to use to show that this is in fact a rational bubble. Because now if we choose alpha to be less than 1 and beta to be equal to 1, recall that then the stable random variables takes only positive values. Plus this proposition here, we can actually show that, it can actually show that this bubble process given by this second component here actually satisfies this rationality condition. So it's a submartingale, and it's strictly positive if this condition here, the last condition here, holds. Okay, so to summarize, what we have done is that now we've gone from like the non-causal autoregressive model to the causal non-causal convolution autoregressive model to make it consistent with the rational expectation model here. So now the question is, okay, how do we study such a model in general? And this model here, although it might not be obvious at first sight, it belongs to a class called the causal non-causal state space model, because what we do is that we observe yt, but we don't observe xtf and we don't observe xtb, right? So we really have like an unobserved component model. We have two components which are unobserved, and then we have one component which is observed. So we have like a causal non-causal state space model. Okay. So now I'm going to introduce the general model briefly. I will not have time to go that much into details with it, but we'll refer you to the paper for more details, and then we can I will discuss this specific model in more details. Okay, so a stochastic process on a general, that takes value on a general measure space, is called a causal non-causal state space model if it satisfies 4 conditions. So first of all, there should be like a causal Markov process that is characterized by some transition kernels and an initial distribution. So this, again, in the example before, this is the fundamental value. There should be a non-causal Markov process, again characterized by some transition kernels and an initial distribution. This is the bubble component before. These two should be independent, and then conditioning on the unobserved Markov processes. What we observe yt is a sequence of independent random variables, right? So you can see basically if we, condition 1 plus condition 4 here is basically like, a traditional state space model or a causal state space model, but now we add a non-causal part, so we need condition 2 and 3 as well. So the question that one should ask in this model here is that, okay, how do we perform inference in such model? And by inference, I refer to, 2 types of inference. I refer to, first of all, state inference, and second of all, parameter inference. So state inference refers to the fact that, as I told you, so we don't observe the x's, we don't observe, let's say, xt right arrow and xt left arrow. We only observe yt, and then we want to draw inference about the unobserved components, right? So in this, specific example that I had above, I want to draw inference about the fundamental value and the bubble based on the price of the spread that I observe. And there are basically 2 cases. The first case is that if these transition kernels here have a transition density, so if the transition kernels of the non-causal Markov process have transition densities, we can basically transform the causal non-causal state space model into a causal state space model and apply standard techniques. However, if the transition kernels of the non-causal Markov process does not have a transition density, but the ones of the causal Markov process have, well, we can transform it actually into a purely non-causal state space model and also perform inference. And I discussed this in details in the paper. But again, like, I'll have to refer you to the paper for details on that. So this is what I wrote here. What I would rather spend time on is the causal non-causal convolution autoregressive model and then the application of it. Yes, so this is basically a recap slide. So again, like we have the yt consisting of 2 components. It consists of a fundamental value xtf, and it consists of a bubble component. So the question is, I haven't really discussed how we can estimate such a model yet. So how we can estimate the parameters of the model, which I will now discuss. So one thing about this causal non-causal convolution autoregressive model is that we can actually not estimate it by maximum likelihood estimation, or it's not straightforward to estimate it by maximum likelihood estimation because the observation kernel does not have an observation density, right? So what you would do in like a traditional state space model is that you need your density for yt given your unobserved components, but this one is a degenerate random variable, right? So it doesn't have a density. So it's not straightforward to estimate it by maximum likelihood estimation. However, the characteristic function of the model is available in closed form, and in the paper I give the expression for this. So we can estimate it by empirical characteristic function estimation instead, which is what we do in the paper, or what I do in the paper. And to briefly introduce this empirical characteristic function estimation, so the motivation comes from the fact that there's a one-to-one correspondence between a distribution and its characteristic function. So the empirical characteristic function estimator basically minimizes a distance between the empirical characteristic or the empirical joint characteristic function and the theoretical joint characteristic function weighted by some weight function here, right? So you can think of it as being like a GMM estimator with an infinite number of, or continuum of moments. And we just compare the empirical characteristic function estimator with the theoretical characteristic function estimator. Motivated, as I said, by the fact that there's a one-to-one correspondence between a distribution and its characteristic function. Okay, so I will spend the last around 4 minutes on the application. So many authors have found evidence of a bubble in the Nasdaq index in the 1990s, which is commonly referred to as the dot-com bubble. So in the paper, I applied the causal-non-causal convolutional autoregressive model to estimate the size of the bubble in both real time, so through a filter, and a posteriori through a smoother, having the traditional, or having this, having the non-causal autoregressive model as a benchmark. So the data is plotted here. So the solid one plots the monthly real prices, and the dashed one plots the real dividends on the Nasdaq index from December 1973 to December 2003. And note the scales are, of the two series are different here. And as you can see, we really see an increase, an exponential increase in the price, which is not backed up by the dividends. And this is also evident when we now consider the spread. So as I said in the beginning, right, I will model the spread instead of the price itself. You see this, so here is the monthly real spreads. You see this exponential increase, and then you see a decrease here. So if we estimate both the causal-non-causal convolutional autoregressive model and the non-causal autoregressive model via the empirical characteristic function estimation, we obtain the following results. So the first row is the causal-non-causal convolutional autoregressive model, and the second one is the benchmark. So we can see here that the fundamental value is quite persistent, and that the bubble actually builds up quite slowly, which is what you expect, right? That the fundamental value is persistent and the bubble builds up like very slowly. Now, if we restrict rho f and sigma f squared to be equal to 0, we see a drastic, decrease in the intercept, so the constant, and we see that the bubble builds up even slower than the one in the causal-non-causal convolutional autoregressive model. Now, as I said, right, I go into the market and observe the monthly real spread. I don't observe the fundamental value, and I don't observe the bubble. Now, I want to estimate them in real time via a filter and a posteriori via a smoother. So if we now look at these two estimations, and here really you can really see that this is still work in progress for this figure here, because this is the filtered bubble, which is in red, and the filtered fundamental value in green, together with the spread in black. And as you can see, so the reason that this is very erratic is that I'm not using very many particles due to computational, because it takes quite a long time to run. But this is definitely something I will look into in the future. But despite that, we really see that the filter actually picks up when we are in this period here. The filter picks up the bubble. So it estimates a positive bubble in the end of the sample, but not a bubble in the beginning of the sample. And this also becomes evident if you look at the smoother, which is, as the name suggests, right, is much more smooth. But the difference between the filter and the smoother is that, again, so the smoother estimate no bubble in the beginning of the sample, but it estimates a bubble in the end of the sample. But it also attributes the increase in the real spreads to an increase in the fundamental value, which is not very clear when you consider the filter here. But this is clear when you consider the smoother. Now, just comparing briefly the estimated bubble in the causal-non-causal autoregressive model with the one in the non-causal model, we see that the former estimates a much smaller bubble than the latter, because we also have a fundamental value. So let me just I'll just stop here, and you can read the conclusion if you zoned out or anything, to leave at least 1 minute for questions. Thank you for your attention.